So, okay, dear colleagues, let us continue our session. And the next talk is by Irina Kuznetsova and Yulia Soroka. This is a joint talk. Irina will be talking. And the title is a realization of groups as fundamental groups of orbits of smooth maps. Please, Irina.
Okay, so let me start with a rough formulation of our main result, and later I will formulate it more precisely. So let MMP be the set of isomorphism classes of fundamental groups P1OF of orbits of Morse maps from M to P. And Sergei Maximenko and Bogdan Fещенko introduced the sets of isomorphism classes B and T of groups generated by direct products and certain rank products. They have proved that MMP includes in B if M is distinct from a two sphere as true and a two torus T true. And M T true R includes in T. And our main results is about that these inclusions are equalities. And moreover, we described some subsets of MMP under certain conditions on the behavior of a map on the boundary of M. So let me recall the definition of the orbit of smooth function. And so let M be a compact surface and dM be the group of C infinity diffeomorphisms of M. Let also P be a real line R or a circle S1. There is a natural right action of the group dM on the space of smooth maps C infinity MP defined by the following rule. And OF is the orbit under such action. We engraft such spaces with Whitney C-infinity topologies, and by OFF, we denote the class component of F in orbit OF. Now, I again recall the definition of the classes about which Sergei Ivanovich already told. So let FMP be the space of smooth maps satisfying the following conditions. The map F takes constant values at each connected component of M, of boundary of M, and has no critical points on it. And the second condition, for every critical point Z of the germ of F, the germ of F at this point is C-infinity equivalent to some homogeneous polynomial without multiple factors. And we also we will call a map F a Morse map if it satisfies condition 1 and all its critical points are non-degenerate. And we will denote by Morse MP the space of all Morse maps. And since the polynomial plus minus x squared plus minus y squared is homogeneous and it has no multiple factors, it follows from Morse lemma that the space of Morse maps includes to the class FMP. Now I will give the definition of these classes B and T, which I mentioned. To do this, we need to introduce the notion of rest products. So let G be a group and M be greater than 1. Then the group Z naturally acts on M's direct product GM by cyclic shifts of coordinates. That is, the following formula hold. And here all indices are taken modulo M. And we can similarly define the actions on the group of the group GMN. So for such group can be regarded as m times n matrices, and we can define the action of the group Z2 Z square on such group by the such formula, which is a two-dimensional analog of this case. And so it's just like a cyclic shifts of rows and columns of this matrix. And notice that both of these actions are non-effective. And now consider such semi-direct products to the above actions. So these semi-direct products are Cartesian products of the sets Gm times Z with the following operation. And multiplication here is defined in a similar way. Such semi-direct products we will call the rest products. So, and now, we also see that these groups are isomorphic. So there is no, there is a different ways to present groups. So, and now I can give a definition of classes B and T. So let B be a minimal class of groups satisfying the following conditions. Trivial group is in this class. If two groups are in B, then their direct product is also in B. And if G in B and N is greater than 1, then G rest products with Z is also in B. And we also can define the class T in similar way. So it is the set of isomorphism classes of groups consisted of groups of the form G and M Z square. And here G is a group from the class B. So it looks like a group generated by trivial group direct products and rest product with Z, and at the end and with rest products with Z square. And as a subclass of B, we also can consider the group A times B with rest products with Z. And here A and B are again groups from B. So, as you see, B0 here is inside B and B is inside G. Okay. And now I will introduce some classes of maps with conditions on the boundary. So notice that for each map F from F and P, we can define the continuous function epsilon F from the set of connected components of the boundary of M to plus minus 1, which will take the value -1 on the boundary component if F has a local minimum on this component, and +1 if F has a local maximum on this component. And denote by epsilon M the set of all continuous functions from boundary components of M to plus minus 1. Now we can define the class FMP epsilon, and for every epsilon, so for every function from components of M to plus minus 1, we can define a subset of FMP which consists of functions map for which epsilon f equals to epsilon. So they have behavior on the boundary the same as this function epsilon. So, and to give next notations, I should recall again notion of Cron-Rodriguez graph. So it is if delta is a partition of a manifold on the connected components of level sets of F, and then the quotient space M over delta is called as a Cron-Rodriguez graph of F. And Bogdan-Feshchenko showed that every function on a torus to R, for each such function, its Cron-Rodriguez graph is a tree or has a unique cycle. And even moreover, previously today he also mentioned that actually it's true for function also to the circle. So and now we can define next notations. So here G X MP epsilon is a set of fundamental groups of orbits of functions where functions are in this class FMP epsilon, and MX MP epsilon is the same for Morse functions. And we also define GPC as fundamental groups of orbits for function on torus to align Cron-Rod graph when a Cron-Rod graph is a tree. And the same is for Morse maps. So if we talk about classes F, we will denote it by G. And if we talk about class Morse, we will denote it by M. So, and here Psi we choose because it looks like tree. So and here correspondingly G0 and M0 are the same groups when gamma has a unique cycle, because this zero is also looks like a cycle. So and so I can now formulate more precisely results of Sergei Ivanovich Maximenko and Bogdan-Feshchenko. So one of the first theorem is about that there is equality between orbits of groups of functions with respect to the diffeomorphisms fixed on a boundary. And in this case, we have that fundamental group of orbit is isomorphic to fundamental group of orbit FDM. So actually we can identify such spaces. And one of the main theorem of Sergei Ivanovich and Bogdan-Feshchenko is the following. So they showed that if M is a connected compact oriented surface distinct from the sphere, then if M is also distinct from the torus, then this class of groups G, D, M, and P includes in B. So all fundamental groups for functions in F and P are in B. And if M is a true torus, then G, C are in T, and G 0 are in B. So So, and our main result is the following. So it's like we show that these inclusions are equality. So it is a realization theorem of such functions. So our main result is the following. Let M be a connected compact-oriented surface distinct from two torus and two sphere, and let epsilon be an arbitrary map from epsilon M. So it transfer connected components of M to the plus minus 1. And then if M is a cylinder and epsilon is constant, which means that it takes the same value on components of the boundary of M, then M dm mp epsilon equals g dm mp epsilon and equals B without trivial group. So fundamental groups for more functions and fundamental groups of orbits for functions from FMP are in this space B without trivial group. And in case if M is a cylinder and and epsilon takes different values on the components of the boundary dm, or M is not a cylinder, then MDM MP epsilon equals to GDM MP epsilon and it equals B. And for the case of a torus, we have the following inequalities. So here MC equals to GC equals to T as a more general class, and M0 equals to G0 equals to B0. Thank you for attention.